Welcome to this lesson on the Doppler effect and its applications. Here we will explore how motion affects the frequency of sound waves and how this phenomena is applied in real life. The Doppler effect is the change in frequency experienced by an observer when either the source of the sound or the observer is moving. This concept helps explain why a siren sounds different when an ambulance is approaching compared to when it is moving away. The Doppler effect can be mathematically represented using the following equation. F prime equal to a product where the numerator V plus V OBS divided by the denominator V minus plus V source, the entire fraction multiplied to F. F prime is the frequency heard by the observer. F is the actual frequency of the sound source. V is the speed of sound in air, which is 343 meters per second, or other medium. VOBS is the speed of the moving observer. V source is the speed of the moving source. Scan the QR code to check out a visual explanation of the Doppler effect. The Doppler effect occurs when there is relative motion between a sound source and an observer. VOBS is positive if moving toward the source, negative if moving away. V source is positive if moving away from the observer, negative if moving toward the observer. Thus, if the source and the observer move toward each other, the observed frequency is higher than the actual frequency. If they move away from each other, the observed frequency is lower than the actual frequency. This happens because sound waves are compressed in the direction of motion, which means increasing frequency, and stretch in the opposite direction, which means decreasing frequency. A real-life example of this is the change in the pitch of a car horn as it drives past you. Let's apply the Doppler effect equation to solve a problem. Mary is on a roller coaster. Her mother, standing on the ground, calls out to her at a frequency of 1000 Hz. However, Mary hears it as 920 Hz. What is her speed? From the problem, we know that Mary is the observer. Her mother is the source. Plus, F prime, which is the observed frequency, is 920 Hz. F, which is the original source frequency, is 1000 Hz. V is given to be 343 meters per second. Now, V source is 0 meters per second as her mother is at rest and not moving. And since Mary hears a frequency lower than the source frequency, it is deduced that Mary is moving away from the source, which is her mother. Here, we choose a negative VOBS. Using the Doppler effect equation and substituting what we know, and upon solving, we determine that Mary's traveling speed is 27.4 meters per second. Now, let's analyze another real-world example involving a moving train. Here's the problem. A train approaches a station at 21.4 meters per second, and the person on the platform hears a trumpet at 3,520 Hz. Given that the speed of sound is 343 meters per second, what is the true original source frequency of the trumpet? From the problem, we know that the person is the observer, while the moving train is the source. Thus, f prime, which is the observed frequency, is 3,520 Hz. F, which is the original source frequency, or the true frequency we are to determine. V is the speed of sound in air, which is given to be 343 meters per second. Now, VOBS, which is actually the speed of the observer, is 0 meters per second, as the person is at rest and not moving. V source is a negative 21.4 meters per second, as the train is approaching and moving towards the observer who is on the platform. Using the Doppler effect equation, substituting what we know, and upon solving, we determine that the true frequency is 3,300.4 Hz. We will also calculate part B, the original sound's wavelength. Recall, V is equal to f lambda, where f is the frequency and lambda is the wavelength of the sound. So the wavelength lambda is equal to V over f, which is 343 divided by 3,300.4, giving us a wavelength of 0.104 meter. For part C, we are to determine the frequency heard by the person after the train passes the platform if the trumpet plays the same note. From the problem, we know that the person is the observer while the moving train is the source. But now, f prime is the observed frequency we are to determine. And f, the original source frequency from part A, is 3,300.4 Hz. V remains the same, which is 343 meters per second, the speed of sound in air. Now, V observer or VOBS is 0 meters per second, as the person is at rest and not moving. Now, V source this time is a positive 21.4 meters per second, as the train is leaving and moving away from the platform, which means it's leaving and moving away from the observer. Now, using the Doppler effect equation, substituting what we know, and upon solving, we determine that f prime is equal to 3,106.6 Hz, which is lower than the source frequency of 3,300.4 Hz. The Doppler effect has several practical applications. One common use is in speed radar. Police use radar speed detectors to measure the speed of vehicles. The device sends out a microwave signal that reflects off a moving car. Due to the Doppler effect, the frequency of the reflected wave changes. And this shift is used to calculate the car's speed. This technology is used in traffic enforcement and is crucial for ensuring road safety. Another key application is weather radar. Meteorologists use Doppler radar to measure humidity by detecting reflected intensity and the speed of clouds using the Doppler shift. This helps predict weather patterns such as storms, hurricanes, and wind direction. Without Doppler radar, accurate weather forecasting will be much more difficult. Let's summarize what we have learned. Characteristics of sound. Sound travels as a longitudinal mechanical wave requiring a medium for propagation. It consists of compressions and rarefactions. Important properties include amplitude, which determines loudness, frequency, which relates to pitch, and speed, which are covered in slides 4 to 10. Comparison between light and sound waves. While both are waves, they have fundamental differences in nature, speed, and the need for a medium, which are covered in slides 11 to 16. Understanding the Doppler effect. The Doppler effect explains how the frequency of a sound changes when the source or observer is moving. We have analyzed two exercises or scenarios where frequency increases or decreases based on motion, which can be found in slides 20 to 25. Applications of sound and the Doppler effect. We have looked at practical uses such as echo-based applications and real-world implementations of the Doppler effect, which are covered in slides 11 to 13 and 26 to 27.